Hello everyone. In this video, I am going to discuss the isothermal process. So this is a process of ideal gas wherein your temperature is constant. Okay, so temperature is constant. So therefore, your change of temperature T2 minus T1 would be equal to 0. So we will discuss formulas, the formulas involved here as we solve these example problems. So number one, we have if 10 kilogram per minute of air are compressed isothermally, so that would be your mass. This is your mass. This is P1, 96 kilopascals. V1 is 7.65, so that is the volume. We're actually volume flow rate. And then P2 is 620 kilopascal. Find the work, change of entropy, and heat for letter A, non-flow process, and letter B, steady flow process. So the steady flow process would have a change of velocity from V1 to V2. So from 15 meters per second to 60 meters per second. So let us first deal with letter A, the non-flow process. Okay, non-flow process. So for the non-flow process, the work is W sub n, and that is equal to the integral of P dV from points 1 to 2. Now we could visualize that using our PV diagram, and since this is compressed isothermally, okay, so meaning to say here you have P1 96, this could be your point 1 and this could be your point 2. Okay, so the pressure increase, and since it's the air is also compressed, so therefore the volume also decreases. Okay, so that would be the movement from point 1 to point 2. Now, we have to remember by principle that the area under this curve, the area always under the curve of PV represents your non-flow work, which is equal to the integral of PdV. Okay? So, or the area under the curve is PdV from points 1 to 2, and in this case, it is the non-flow work. So, how are we going to solve that? From our pressure volume temperature relation, we have PV is equal to C. Then therefore, our P here, our pressure, would be equal to your C over V. So if we substitute that to our integral, P is C over V times dV. So your C will come out of the, or will be written before the integral. So you have dV over V. But your C is equal to PV. So it could be P1 V1 or P2 V2. So it depends on the combination that is presented in the problem. So let's just say P1 V1. Alright. And then we have the integral of dV over V. The integral of dV over V is ln V. And then applying the limits, so this would be ln V2 minus ln V1. And by properties of logarithm, we now have W sub n is P1 V1 times ln of V2 over V1. So again, this could also be P2 V2 times ln of V2 over V1. So that is your non-flow work. So we have P1 V1, that is given. What we don't have here is our V sub 2. So we first have to solve for that. And to solve for that, we will use our PV is equal to C. P1 V1 is equal to P2 V sub 2. And here, V sub 2 would be equal to P1 V1 over P sub 2. So pressure 1 is equal to 96 kilopascals. Kilopascals is kilonewton per square meter. V1 is equal to 7.65 cubic meter per minute. And then P sub 2 is equal to 620. 620 kilonewton per square meter. Okay? So of course, kPa or kilonewton per square meter would cancel out, and we would have volume as cubic meter per minute. So let's get our calculator. We have 96 times 7.65, then divided by 620. So 1.18. So this is 1.18 cubic meter per minute. So we go back to our W sub n. W sub n would be P1 is equal to 96 kilonewton per square meter. Then V1 is 7.65 cubic meter per minute. And then ln of V2, so we have just solved for that, 1.18 over 7.65. So no need to write because it's a ratio and the units would be cancelled. Okay? So let's get our calculator. We have 1.18 divided by 7.65. Let's get the logarithm of that. Natural logarithm. Then we multiply 7.65 times 96. We have 1369.93. So negative 1369.93. Now what is the unit? So we have here square meter would be cancelled out. And we have kilonewton meter per minute, or kilonewton is simply kilojoule. So kilojoule per minute. Okay, so that would be our non-flow work. Now since this is negative, no, meaning to say that work is done on the system, or work is done on air. Okay, right? So that is your non-flow work. So what else? We are also asked to solve for the change of entropy and the heat. So change of entropy. So the change of entropy would would come from Q over T. Okay. Now why is that? So the diagram that we are going to consider there is our TS diagram, and let's just say that since temperature is constant, then therefore we have this points 1 and 2 and a horizontal line, no, going from point 1 to point 2. Now the area under this curve would represent your heat. Okay, and this one would be your delta S. So as you can see, the area under the curve is the heat, so therefore Q, or our heat, would be equal to delta S times T. Okay, delta S times T, and then therefore delta S would simply be equal to Q over T. Okay, but what is our heat? Okay, what is heat? Our heat for a isothermal process would be equal to your non-flow work, since your delta U. So heat is non-flow work plus delta U, or the change in internal energy, but the change of internal energy is zero. Okay, for an isothermal process, your delta U is equal to 0, change of internal energy, and also your delta H is equal to 0. Remember that the formula for delta U is mCv delta T, and delta H is mCp delta T. But since delta T is 0, so therefore these two would also be 0. Alright? So Q is equal to the non-flow work, and we know that the non-flow work is equal to 1369.93. So if you will just follow the solution here, your delta S would be equal to Q over T, and we have negative 1369.93 kilojoule per minute divided by T. Okay, but we don't have the T, or we don't have a temperature given. So a workaround for that problem would be coming from your non-flow work formula. And your non-flow work formula is P1 V1 times the natural logarithm of V2 over V1. So let's just write that down first. Your non-flow work is P1 V1 times the natural logarithm of V2 over V1. This is your non-flow work, and we have established that your non-flow work is equal to Q. That's why we use the non-flow work divided by T, but the problem is we don't have the T. So if we will substitute that for the formula of delta S, so we'll have P1 V1 ln V2 over V1, that is your non-flow work, which is equal to Q, so over T. Now notice here we have P1 V1 over T, and that P1 V1 over T would simply be your mass times the gas constant from the perfect gas law. Okay, so if we will substitute that, we can already solve for delta S, and delta S is equal to mR times the natural logarithm of V2 over V1. Alright, so that's a parang workaround, no, for the formula of delta S, which is equal to Q over T. So we're given the mass. Mass is equal to 10 kilogram per minute. So 10 kilogram per minute. We have it as 0.28708, and this would be kilojoule per kilogram Kelvin, and then times the natural logarithm of V2 over V1. So V2 is 1.18. Let me just check that. Yes, 1.18, and V1 is 7.65. Oops, 7.65. Right? So the unit, kilogram cancels out. So the unit is kilojoule per minute Kelvin. Okay? So let's get our calculator. So we have 1.18, unahin na natin yun, divided by 7.65. Then the natural logarithm of that ratio times 0.28708, then times 10. So you have negative 5.36, or let's just say negative 5.37. So delta S is negative 5.37 kilojoule per minute Kelvin. So that is your change of entropy. And finally, heat. As I've said kanina, heat is equal to your non-flow work. Okay, remember this formula. Heat is equal to your non-flow work. Then therefore, Q is equal to negative 1,369.93. So let's just write it down, kasi hinahanap din naman siya. Negative 1,369.93 kilojoule per minute. Okay? So we have already the heat, the change of entropy, and the non-flow work. Now that is for letter A, which is the non-flow process. Okay? This one, non-flow process. So letter B, steady flow process. So let's just have a quick review here. When we say non-flow process, this is applicable to closed system. So this is applicable to a closed system, and for letter B, steady flow process, so mean to say this is an open system. Now an open system would have the mass, so here air, would have air entering and leaving the boundary of the system. So ang gusto lang dito ng problem is what if it's a flow system, letter A, and what if it's a steady flow system, or what if it's a open system? What would be, given the same parameters, what would be the work, change of entropy, and heat? No? So let's go to letter B. So letter B, we have the steady flow process. Okay, so for the steady flow process, our work would be equal to W sub S, no? Yan yung symbol niya, W sub S. Napalitan lang ng subscript from W sub N to W sub S. But the formula there would be equal to the negative integral of V dP minus delta K. So this one has a limits of 1 to 2. So first, let's evaluate what is this negative VdP. Okay, so negative VdP, the integral of negative VdP from 1 to 2. Now, our V, okay, we could get that substitution from PV is equal to C because it's an isothermal process. So therefore, V here would be equal to C over P. So if we substitute that, we'll have negative C integral of, so dP over P with limits from 1 to 2. So C is equal to PV, and PV could be P1V1 or P2V2. It's up to you. So negative P1V1, and then integral of dP over P is simply ln P. Okay, so apply the limits from point 1 to point 2. So if we apply the limit, then this will be negative P1V1 ln of P2 over P1. Now P2 over P1 can be in terms of your volume, of your ratio of volume, from P1V1 is equal to P2V2, your P2 over P1 would be equal to V1 over V2. So let's just change this one, and I would like to make a point here after substitution. So this will negative P1 V1 ln of V1 over V2. Now the negative here can be the exponent of your ratio of V1 over V2 by properties of logarithm. So that would be P1 V1 ln of V1 over V2 raised to negative 1. So if it's raised to negative 1, then therefore P1 V1 ln V2 over V1. And we have already encountered this formula for the non-flow process, and that is actually equal to your non-flow work. So therefore, we can conclude that if you are not given the change in kinetic energy, your steady flow work is also equal to your non-flow work. Okay? So, let's just write that formula here now. Ws would be equal to this one, and this one is evaluated as P1 V1 ln V2 over V1, and then minus delta K. But we don't need to solve for this part of our equation because we have already solved for that as our W sub n a while ago. So that is equal to negative 1369.93. Negative 1369.93 kilojoule per minute. Now delta K is the change of kinetic energy. So that is K2 minus K1. And essentially that would be equal to m over 2k times the difference between the square of V2 and V1. Okay, V1 squared, right? So let's just change that one. Okay, V2 squared minus V sub 1 squared. So let's input that here. So we have minus m is equal to 10 kilogram per minute. So 2 divided by 2, and then K would simply be 1 kilogram meter over Newton second square. Now the difference here is simply 60 squared minus 15 squared, and that would be meter square per second square. So second square cancels out. Also meter would be cancelled out. So what we'll have here is also kilogram. What we'll have here is Newton meter per minute. Now, the unit for our first term is kilojoule, so therefore, we simply have to divide this by 1000 in order for us to obtain kilojoule, no? Using 1000 joules, okay? 1000 joules is 1 kilojoule, okay? So joule is Newton meter, so canceling Newton meter, and the final unit would be kilojoule per minute, okay? So pares na sila, you could already subtract it. So subtract them from each other. You could perform the operation. So this one, let's solve for that one first. We have 10 divided by 2000, and then times the difference of 60 squared. 60 squared minus 15 squared. Close quantity equals 16.88. Okay, so we have here negative 1369.93 minus 16.88. Okay, so plus 1369.93. So we have 1368 negative 1386.81. 1386, not 68. 86.81. Okay, kilojoule per minute, and that would be your steady flow work. Okay, let's just box that down. Now, how about heat and entropy? No, so if we go back to our energy equation, we have heat is equal to, so this is in chapter 2, no, energy equation. Heat is equal to delta P plus delta K plus delta H plus your work. So in this case, because it is a steady flow work, so W sub S. Now, we could assume in this problem that your delta P is 0 because there's no given position. Delta K, it has a value, and delta H is 0 as I've explained. That is 0 because your change of temperature is 0. Now, your W sub S, so we have delta K. Your W sub S is P1 V1 ln of V2 over V1 minus delta K. So, to get Q, no, to get your Q, it is simply equal to P1 V1 ln V2 over V1. So, in this problem, your Q, your heat for steady flow process and for the non-flow process would be the same. Okay, so Q is equal to, it's also 1369.93 kilojoule per minute. And since that is your Q, so therefore you'll also obtain the same delta S. So delta S is equal to, so the same, no? Negative 5.37 kilojoule per minute, and then we have Kelvin. Okay, so in this problem, let's just summarize this problem. We have heat is negative both for steady flow and for the non-flow process. So we could say that heat is rejected. So let's just write it down. Okay, it is rejected by air. Okay, and then since heat is rejected, you have your work is also negative, so work done on the system. Okay, so saan na yung W sub S, this is negative, so work done on this system. Okay, so let's just write it also here. So your Q here is also rejected by air, and your W sub N is 1. Okay, I have already wrote it down. Work done on the system. So let's go to our next problem. So problem number 2, nitrogen at an initial state of 300 Kelvin and 150 kilopascals and zero point 0.2 cubic meter is slowly compressed or compressed slowly in an isothermal process to a final pressure of 800 kilopascals. Determine the work done during this process. So as I've told you, the work done here would be equal to your P1 V1 times the natural logarithm of V2 over V1. So an alternative formula here is we could replace V2 over V1 by pressure, and that is because we have P1 V1 is equal to V sub 2 V sub 2. Therefore, V sub 2 over V sub 1 would be equal to P1 over P2. So another formula that you could use is P1 V1 then times ln of P1 over P2. Okay, so since so we don't have to solve for the V sub 2, okay, because we could replace V sub 2 over V sub 1 by P1 over P2. Okay, so non-flow work is equal to P1. So P1 is 150, that is kilonewton per square meter, and then V1 is 0.2 cubic meter, and then times the natural logarithm of P1 over P2. So P1 is 150 again, 150 over 800. So let's get our calculator. So we have 150 divided by 800, and then let's get the natural logarithm of that multiplied by 0.2 times 150. So we have negative 50.22. Negative 50.22. Now the unit here, as you can see, since we could cancel square meter by cubic meters, we have kilo Newton meter, or that would be kilojoules. Okay, so if the problem would ask you to solve for the heat, so the heat would simply be equal to your non-flow work. Now remember that Q is equal to non-flow work plus delta U, and delta U in an isothermal process is equal to 0. Therefore, Q is equal to W sub N. Okay, so just in case that the problem also requires the non-flow work is also equal to your heat. Now, it's important to take note here that this is negative. So therefore, work is done on the system. Okay, so let's just write this down. Work is done on the system. Okay, so problem number 3, we have a piston cylinder device initially contains 0.4 kilogram of nitrogen gas at 160 kilopascals and 140 degree Celsius. Now the nitrogen is now expanded isothermally to a pressure of 100 kilopascals. So determine the boundary work done during this process. Now here we were introduced to a new term, no? Boundary work, but it is also work non-flow. Okay, that's also non-flow work, or it could also be your steady flow work. Now remember, these two are equal because we have established that the integral of PdV with limits from 1 to 2 is also equal to the negative integral of VdP. So unless there is delta K, or there is a change in kinetic energy or change in potential energy, then we're talking about the same thing. Your non-flow work would be also your steady flow work. So the work here, whether it's a closed system or open system, would still be equal to P1 V1 times the ln of V2 over V1. So here we're given the pressure. Okay, we're given the pressure, and we're given the temperature, the mass, okay, and also P sub 2. Okay, so what we don't have here is our volume. Okay, but we are given the mass, so let's just write the given down. We have mass is equal to 0.4 kilograms, and P1 is 160 kilopascals, and T1, so let's just write T1 140, and we need to add 273 there. So 140 plus 273 to make it absolute. So we have 413 Kelvin. Okay, and then we have P2 is equal to 100 kilopascals. So work, we have P1, we don't have B1, but using the perfect gas law, we have P1 V1 is equal to MR T1. We could solve for V sub 1. So V sub 1 is equal to MR T1 over P sub 1. Now the question now is, what is our R? So our specific gas constant for nitrogen, because this is nitrogen, says here, nitrogen gas, our specific gas constant is equal to 0.2968, okay, kilojoule per kilogram Kelvin. So let's input the given. We have mass is equal to 0.4 kilograms, and then R 0.2968 kilojoule per kilogram Kelvin times T sub 1. So T sub 1 is 413 Kelvin, and then over P sub 1, 160 kilopascals. So kilopascals is kilonewton per square meter. So your kilogram will cancel out, your Kelvin will cancel out, and this one, kilojoule, is kilonewton meter. So kilonewton cancels out, and then this square meter will be multiplied here for a final unit of cubic meters. So V1 will be equal to, so we have 0.4 times 0.2968 times 413, then divided by 160. So the answer is 0.306 cubic meter. So there's a formula. In our formula, we have P1, V1, and then ln V2 over V1. Now, we don't have to necessarily solve for V sub 2, because, again, the alternative formula there is that you have your work is equal to P1 V1, and we could replace V2 over V1 by P1 over P2. Okay, and that is, again, from the relation P1 V1 is equal to P2 V2. No, if you would solve for V2 over V1, it would be equal to P2 over P1 over P2. So that's why you can do the substitution. So for pressure 1, we have 160 kilopascals. So that is again kilonewton per square meter. And then V1, 0.306 cubic meter. And then the natural logarithm of 160 over 100. So calculator, we have 160 times 0.306, and then times, let's just do 160 divided by 100, then natural logarithm of that. Okay, so we have 0.47. Let's do that again. Let's first have 160 divided by 100. Okay, So again, 160 divided by 100. Then let's get the natural logarithm. Yun, times 0.306 times 160. So we have 23.01. So your work or your boundary work, sabihin natin W sub B is equal to 23.01 kilojoule. Now why kilojoule? Again, square meter cancels out and we have kilonewton meter as your kilojoule. Okay, so I hope you have learned something from this video regarding the isothermal process. And just a recap, no? Just a recap, your non-flow work would be equal to the integral of PdV, and that would be equal to P1 V1 ln V2 over V1. Your steady flow work would also be the same as your non-flow work, provided that your delta K is equal to 0 and also your delta P is equal to 0. Your delta S would be equal to mR ln of V2 over V1, and then that's your change of entropy because that comes from the formula Q over T. Now your delta U and your delta H are both equal to 0 because the change of temperature is 0. And then again here, you just have to emphasize your Ws is equal to your Wn minus your delta K if your delta K is not equal to 0. So thank you for watching.